So today I want to start computing some correlation functions. So we've set up all the machinery, most of the machinery that we need. There's one still that's outstanding, and that's the finite version of the Ward identities, which we're going to use extensively. And then once we have the Ward identities, recall these are constraints that the correlation functions need to satisfy. In our case of the conformal field theory, these will turn out to be a differential equation or differential equations that the Ward identity, that the correlation functions need to satisfy, right? And that's because essentially what we're going to do is we're going to take these correlation functions and impose constraints on them coming from the conformal symmetries, from the action of the generators of the conformal group on this. Now, one of those generators that's very important for us is P mu, and P mu acts as a derivative. So that converts these constraints into differential equations, which we need to solve. And we'll start off with the simplest case of the quantum average of a single primary operator. This will be the one-point function. We will then move on to, this will be relatively straightforward because most of the constraints will turn out to be degenerate. And so we really only need to impose one, possibly two constraints on them. There are four constraints that we're going to be imposing in general. And I'll show you how this works with the two-point function. The two-point function is, of course, what you might otherwise call the propagator or the Green's function. So it's an important step in this calculation, right? So that's the main brunt of this calculation. And really, most of the heavy lifting will go into computing the two-point function and showing you how the conformal transformations completely determine the two-point function in terms of the conformal weights of the operators. Once we've done this for the two-point function, we will have set up everything we need for the three-point function, which is similarly highly constrained by conformal invariance. And then we'll move on to just stating the result for the four-point function now. And if we have time, I will return to this using to show you how you can use the shadow of formalism to write down the four-point function in terms of hypergeometric functions. Okay, and that's essentially because the Ward identities for that case becomes a hypergeometric equation. Okay, so let's go through systematically the constraints enforced by the Ward identities on the one and two-point functions. So by way of recalling where I left off last time, because I probably rushed through the last step, recall that the Ward identity that we wrote down was that the sum over, let's say, I equals 1 to n for an n-point function. An n-point function, remember, is the product of n operators, each with their own conformal weights, and in general, each with their own Lorentz spin indices. And then I take the average of this over the quantum system, which is to say, I sandwich this product of the operators between the vacuum states. And I'll remind you that we're specifically interested in symmetries that are not spontaneously broken, which means that the action of the generators of that symmetry on the vacuum state leaves the vacuum state invariant. So what we found was that O1, A1, X1 due to delta O I, AI at XI due to O N, A N, XN must be 0. And remember, the statement here is that this is the variation, this is the small change that we're making that's induced on the operator by making the change x going to x plus delta x, where delta x is a conformal transformation. Okay, so what I do here is sum over all the possibilities of removing a particular operator and replacing it with the delta of that operator, right? And this must sum to 0. So this is the Ward identity. The infinitesimal version of the Ward identity. We've derived this before using the path integral, so it's not something that should be entirely unfamiliar to you. What I will say, though, is that at no point in our derivation of this identity did we say anything about conformal transformation. So this is a general statement. Okay, if I make a transformation on the xi and they induce some transformation on the operator delta O, then it must satisfy this identity. So this is the Ward identity is a general set of constraints that we impose on the system, right? We're going to, in addition, impose that those transformations must be conformal transformations, but they won't change the form of the Ward identity. So the Ward identity statement. Okay. Again, this was a finite version. This was an infinitesimal version of the Ward identity. In a conformal field theory, these deltas will turn out to be differential operators, and so the Ward identity will turn out to be a differential equation that our correlations must satisfy. So obviously, the question that you could ask is there a finite version of this of the Ward identity? So for a finite version of the Ward identity, let's consider the finite transformation O at x going to O tilde at x tilde is related to O by U of G O at x U dagger at G. In this case, our endpoint function this guy here, O1, A1 at x1 due to O n, A n, xn. Again, sandwich between the vacuum states. And we do what we did the last time, which is to insert the identity because these are Hermitian, these are unitary operators. So we insert the identity everywhere in between here and here. So this is U, sorry, O, U dagger of G, U of G, O1, A1 at x1, all the way through to O, A-N, U dagger U. And then we said last time, the same is true here, that because this is a symmetry that's not spontaneously broken, the action of the generators leaves that invariant. And so this is just the same thing as U of G O1 A1 at X1. And then there will be a U dagger on the right of it. And this will go all the way through to U of G O N A N at Xn, U dagger of G acting on the vacuum. Okay. But then this combination of U, O, U dagger is nothing but the transformed operator. So this is O1 A1 at X1 tilde tilde all the way through to O N A N tilde at Xn tilde on the vacuum. And this is what we're going to take to be the finite version of the water identity, namely that this correlator here, this endpoint correlator, must be the same as that endpoint correlator. Okay. I need to make one final remark as a preliminary remark before we actually go ahead and calculate correlation functions, and that's to tell you, well, that's to recall how a primary operator transforms, namely as a tensor density, right? Meaning that there's a Jacobian factor that that enters the transformation. So if I have a primary operator labeled by some conformal dimension, then it transforms to O delta, some conformal dimension delta, then it transforms to O tilde, again of A of X tilde, and this is equal to dx bar to the delta over D, where D is the number of space-time dimensions, L A B, where this is some matrix that tells me how the indices of the Lorentz indices transform. Namely, you know, this doesn't necessarily need to be a scalar. It could be a vector. It could be a spinor. It could be a general tensor like the energy momentum tensor. And this matrix will tell me how those indices will transform. And then what's left is OB delta of X. Okay, so this is a tensor density. That's how tensor densities transform. If you recall what you learned in GR, this matrix transforms the Lorentz indices. This is the conformal dimension of the operator. And this is the Jacobian of the transformation. Because we're going to need it in what follows. Let me just write down some of the Jacobians that we're going to use. I'm not going to prove these. We've proved the one for dilatations before. The rest followed in the same way. But we're going to need these, so I'm going to write it down. So for translations, dx by dx tilde is the identity. For rotations, again, dx by dx tilde is the identity. So just one, this is a determinant, it's a number. Dilatations, dx by dx tilde is lambda, which is the thing that we scale everything by, to the minus the dimension of space-time. So this space-time dimension. Yeah.
So I have a question. So with regards to the finite water density, what does it do for us when you contrast it to the infinitesimal version of the water density?
We're going to do lots of examples, and it should become clear when we do the examples what it does for us. Okay. Inversions have the Jacobian equal to 1 over x tilde squared to the d. Okay, so that was equation 3, 4, 5, 6, 7. Okay. So this is all the ingredients that we need. So what we're going to do is, again, following the logic that we've been using previously, we're just going to think about scalar primary operators. Right? Scalar operators, because I don't want to worry about this LAB, but we'll do some examples later, maybe where we'll look at things that are not just scalars. And primary operators, because once I know how the primary operators transform, once I know what the correlation function for primaries are, then I can immediately compute the correlation function for their descendant operators by just taking derivatives. Okay, so these are the basic things that we want to work with. They're the simplest and easiest to understand. So let's compute O delta of x. So this is the 1-point function for a scalar primary operator with conformal dimension delta. Okay, so what we want to do is start off by, well, first thing is, I don't want to actually calculate this thing, right? If I wanted to actually calculate this thing, then I would work out the path integral and I would do the calculation using the path integral, right? That would require me to specify for you an action. So I'd have to pick a particular conformal field theory. to work with, right? I'd have to show you that the action is, well, we've done this already, but in principle, you'd have to show that that action was conformally invariant. You'd take that action, you'd calculate the path integral, you'd insert this operator into the path integral, you'd then normalize by the path integral itself, you'd do the calculation, you'd calculate whatever Feynman diagrams you need to calculate, and you would get whatever answer you get. Okay, I want to show you that whatever we're going to calculate here holds for all conformal field theories. Okay, I'm not telling you which dimension it holds in all the dimensions, right? This is the power of the conformal symmetry. Okay, so we want to calculate this object for scalar primary with dimension delta. The point is that I want to take this guy and I want to impose all of the symmetries, the conformal symmetries on this, right? And then use the Ward identities to constrain it. And I'm going to show you just how constraining the Ward identities are. Let's start off by translations. Again, this is a scalar primary, and we wrote down how primary operators transform under any one of these transformations. So in particular, if I lose the A index, that tells me how a scalar primary will transform. So under translation, the scalar primary transforms to delta O delta of X. So again, I'm using I'm using the conformal dimension as a label of the operator. And this is just A mu d mu O delta of X. Okay. One second. So since this is a one-point function, the Ward identity reads as follows. Namely, that A mu d mu O delta of X must equal to 0. There is only one operator. I take that operator out, I replace it with the delta. The delta is equal to A mu d mu of O. And so the Ward identity tells me that this must equal to 0. In other words, and because this must be true for any infinitesimal vector A mu that parameterizes the translation, this implies then that d mu of O of X must equal to 0, which then means that O itself, or the one-point function, must be a constant. Right? The question is, can we determine this constant? And the answer is yes. And to determine the constant, what we do is we impose the rest of the symmetry. We have to impose 4 symmetries on this one-point function, and we have to show that it's invariant under all of those symmetries. So we've done translations, and the restriction that translation gives us is that the one-point function must be a constant. So to determine what that constant is, we're going to impose invariance under, or we're going to implement the scaling transformation. Namely, we're going to send x to lambda x. Right, so we're just going to scale the length in our theory by some number, lambda. Well, under a scaling transformation, the operator, the scalar primary, goes from O of x to O tilde. So O delta of x goes to lambda to the delta of O of lambda x. Right? So this we worked out last time. In which case, the following is true. The 1-point function O of x, the 1-point function of O of x, again, and this answers your question, by the finite version of the Ward identity must go to O tilde of x tilde, okay, by equation 2. Which is just the 1-point function of lambda to the delta O of lambda x. Yeah.
So if you put that up there and you plug in the Jacobian for the theta over there, where do you come up with the negative?
The minus d. That's lambda, yeah.
So I think maybe what might be happening is that Jacobian there, I think it's Jacobian the inverse transformation. It's got a derivative.
Yes. Yeah, I think it is. That's right.
And these are also with respect to the inverse transformation.
That's right. I think this should be.
If we leave it like this sign, is that will affect the inverse transformation, like as the notation is written there, capital X. So what is the Jacobian affect the inverse transformation?
Oh, I see what you're saying. Yeah. So this should be a. Yeah, and that makes sense with regards to the x tilde and x's placement there as well. Okay, good. So, all right. So I can pull this guy out, the lambda to the delta. So that's just lambda to the delta times the 1-point function O delta lambda x. On the left-hand side, this is just c that we found, that constant. And on the right-hand side, this is lambda to the delta times c. Okay. In other words, for the Ward identity 2 to be true, which it is, I need that c times 1 minus lambda to the delta equal to 0. All right. And this is true in for two cases. Either c is 0 or lambda to the delta is 1. In other words, delta is 0. Okay. So this means that either delta is 0 or c is 0. Okay. Delta equals 0 corresponds to the identity operator. Okay. And the identity operator obviously commutes with all the generators of the transformation, trivially, right? In particular, it commutes with the generator of special conformal transformations, K mu. And anything that commuted with the generator of special conformal transformations we call the primary operator. So in this sense, the identity operator is trivially a primary operator as well. Okay? It also commutes with p mu. Again, trivially, right? And commuting an operator with p mu is what generated descendants for me, right? So this guy commutes with k mu, so it's a primary, but because it commutes with p mu as well, it's a primary without descendants. Okay? In other words, the identity belongs to a conformal multiplet, but it lives there by itself. However, this sad story aside, that this guy lives in his family all by itself, what we have found in this statement is that if delta is not equal to 0, then the 1-point function must equal to 0. Okay? Again, if I wanted to calculate this thing, this object, I would have to calculate some path integrals. I would have to calculate two path integrals, in fact. The path integral for the normalization that sits in the denominator, and the path integral with the insertion of O that sits in the numerator. And when I do that, I will find that it's 0. Right? But it's a lot more work. And Cameron's not here, but Cameron did my course last year, in which we did the work. And it came out to be 0 as well, but it took like 2 lectures to show that it comes out to be 0. And that's the trivial one, right? So what we have found at the level of the 1-point function, and again, this is the trivial one, right, is that just imposing the symmetry transformations and the Ward identities was enough to completely fix what the 1-point function is. It says that the 1-point function vanishes. Okay. What are we on? 10. Oh. Now, you might say, but hang on. In fact, let's put this down as some notes and take stock of what we've done. The first point to note here is that you might say, hang on, I've been emphasizing so far that I need to impose all the symmetries, right? But I've only imposed 2. Translations, 2 out of these 4. Translations told me that the 1-point function has to be constant. Dilatations told me that that constant has to be 0, right? Or delta has to be 0, right? What about inversions and rotations? Well, it turns out that inversions and rotations don't contribute any more information to the story. They give me the same information, okay? So even though I haven't imposed inversions and rotations, they act trivially. The remaining transformations act trivially. And don't contribute any more information. And the second point to note is that this result holds for all conformal field theories. Right? We don't need to know anything about the system, the Hamiltonian, the Lagrangian, the action, the dynamics at all, only that it has conformal symmetry.
So there's point number one, but I decided to consider other view we get to the same result as we just did now.
Yeah. Okay. Okay, that's all I wanted to say about the 1-point function. So now let's start the calculation for the 2-point function. I'm probably not going to finish it because the next lecture is going to come in, but let's see how far we can get. All right, so now let's do the same, let's play the same game for the 2-point function. And I'm going to assume that these guys have different scaling dimensions. Okay, so O1, X1. I'm still going to talk about scalar primaries, so there's no Lorentz indices. And the 2 points that we're talking about are this X1 and X2. Okay, so this is the 2-point function for scalar primaries of dimensions delta 1 and delta 2. And we want to know if conformal symmetry, if we can get lucky again, and conformal symmetry completely fixes this object. The answer is yes. Just to spoiler alert. So we'll again start with translations. So under translations, by the same vector, A mu, the operators transform as O delta 1 at X1 equal to A mu D I should be specific here. So D by dx1 mu O delta 1 at X1 and delta O delta 2 of X2 is A mu D by d mu X2 O delta 2 at X2. The Ward identity reads as follows. Remember, now it's a sum of two 2-point functions. In the first one, in the first term, I replace O with delta O. In the second one, I replace O at X2 with delta O at X2. Okay. And then I sum these guys. So it's A mu D by d X1 mu O delta 1 at X1 times O at delta 2 at X2 plus O delta 1 at X1 A mu D by dx2 mu O delta 2 at X2 and all of this must equal to 0. And again, this must hold for any vector a mu, which means that the following is true. D by dx1 mu plus d by dx2 mu on O delta 1 at x1, O delta 2 at x2. By the way, these functional dependencies here, I mean x1 of x1 mu and x2 mu, right? Just such a big thing. But the point is that this derivative acting on the 2-point function must vanish. This is what I meant when I said that the water identity converts that constraint equation into a differential equation that must be satisfied. So this is the differential equation that must be satisfied. So now, keep in mind that this guy is a function that takes two numbers as inputs, x1 and x2, two positions in spacetime as inputs, and it chucks out a number, right? And it outputs some number. In other words, it's just a function of x1 and x2. Okay? Let's call it number f of x1 and x2. So this guy is a function of x1 and x2. All right? And our job is to determine what that function is. Well, what this equation tells us, though, is whatever that function is, it must satisfy that d by dx1 of f of x1 and x2 must be minus d by dx2 of f of x1 and x2. In other words, whatever this function is, its dependence on x1 and x2 can only go like x1 minus x2. It can only depend on the difference between these two functions. Okay? I mean, if it's not clear a priori, one way to do this is to convert to two new functions, let's say u and v, that are x1 plus x2 and x1 minus x2, and you'll show that the u dependence falls out from this equation, so it can only depend on v, and v is x1 minus x2. So this necessarily means that f of x1 and x2 is actually f of x1 minus x2. So it can only depend on the difference between these two. And I'm going to stop here with equation number 12. Right? So again, translations tell us that whatever this function is, it can only depend on the difference between those 2 points in space and time, in space-time. Right? What I'm going to show you next time, Monday, is that the immediate thing that we can show after this is that implementing rotations, or more generally Lorentz transformations, tells us that not only must it depend on the difference between these 2 points in space-time, it can only depend on the distance between these two. Right? So mod x1 minus x2. Okay, and then we'll take it from there. All right, so let's stop here.